Okay, let's consider another type of mass spectrometer, which is ion mobility spectrometer. Actually, this is not a real mass spectrometer. The principle is quite similar. Okay? It is called ion mobility spectrometer. Okay? You will see the electrophoresis, okay, in subsequent chapters, and this is very similar to that technique. And between the electric field here applied between here and there, the ions are moving toward to the right hand side, yeah, and then the mobility of ion here in this well not in a solution, yeah, is this is gas phase, in this gas phase, okay. So the ion mobility are different depending on the size of ion and the charge on the ion, okay. But this is quite useful because it is operated in air at ambient pressure, okay. Okay, let's see how it works. So first, you put your sample here, okay. This is sample disk, yeah? And this is dissolved heat, okay. And you input here through this port the sample carrier gas, okay. And in a sample, your samples on your disk is dissolved, yeah, by this heater, and then, yeah, these are your sample molecules, okay. And this sample is passed through the here, yeah, between this nickel 63, yeah. This is as radioactive species, yeah. It emits beta electrons, okay. And here, so sample carrier gas is air, but it contains reagent gas, the chlorine gas Cl2, okay. With the Cl2, and then this your sample is carried away with the Cl2 in air, and then it is ionized while it passes through this part, okay. It emits beta electrons, okay. And then here the ions are moving, okay, toward the detector, okay. And the ion mobility, yeah, as I said, depends on the size of ion and the charge ratio, okay. Yeah, and it is detected here. But one of the characteristics of this spectrometer is that it operates at an ambient pressure, so you don't have to apply in a high vacuum here in this region, yeah, which is called drift region, okay. It's the ions are drifting, okay. It attracted to the to the detector, okay. Yeah. So this is kind of electrophoresis. You see the electrophoresis is the ions in solution are moving in under the influence of electric field, okay. And depending on charge and the mass, and the ion mobilities are different, okay. Here, ion mobility spectrometry does not measure molecular mass and provides no structural information, okay. And ion mobility spectrometry is a gas phase electrophoresis, okay. Electrophoresis, but not in solution phase, but in gas phase, which separates ions according to their size to charge ratio, Unlike mass spectrometry, ion mobility spectrometry is capable of separating isomers. Yeah, this is quite, this is peculiar. An electric field of 200 to 300 volt per centimeter. Yeah, this is electric field intensity in the Dirichlet region. Here this is Dirichlet region. Is established by potential difference on the Dirichlet rings. The field causes either cations or anions to drift to the right at the speed 1 to 2 meter per second. Since this is operated at ambient pressure, and this is quite widely used, especially in an airport, to detect harmful substances like drugs or explosives. Okay. Yeah, this is the kind of spectrum. Okay, and as you see many peaks. Okay, and this is a negative ion mobility spectrum of explosives. You see the many this abbreviates, RDX, TNT, PETN, and so on. Those are the explosives. Okay? And here this calibrant, this is internal standard. Okay? And here you used this spectrum was obtained with Cl2. This is the reagent gas. Yeah? This gas is contained in air. Okay? And then you see many peaks, but these peaks, the first two peaks are the water molecule, the kind of aggregate, okay, with Cl minus ion, okay, and since this one has only -1 charge, and the size of the let's see, the size is we don't know yet how big is the charge, but it is detected at this the millisecond, about 7 milliseconds, and then this peak was identified. This water molecule, the kind of aggregates in air, with this one O2 minus, right, and like that. And this peak area is proportional to the number of ions. Peaks are identified by their mobility. Okay, so you need a standard spectrum, which is reproducibly measured relative to that of internal standard. This is internal standard. Runs are repeated 20 times per second. The display spectrum averages many runs and require 2 to 5 seconds to obtain. Actually, this is quite rapid measurement. Okay? Detection limits are 0.1 to 1 picogram for compound with favorable ionization chemistry. Yet the idea is that although you don't measure the mass, but you ionize your sample with chlorine, and here using this one, this nickel beta electrons emitted from this nickel isotopes. Okay, and then now let's move to the different the topic, chromatography and mass spectrometry. Usually chromatography is combined with mass spectrometry because the chromatography does the separation. Okay, you have a mixture, and then you want to detect, or you want to separate first, and then the separated species are detected by mass spectrometry. Right? Since chromatography is very, very useful to separate the the mixture very efficiently, and then each separated species is detected by mass spectrometry, right? Since mass spectrometry is one of the most sensitive analytical technique, right? The combination of these two techniques are very powerful to detect extremely small amount of species. Okay? And there are many types of chromatography, but you'll see soon. But capillary column used in gas chromatography is connected directly, directly to the inlet of a mass spectrometer. Otherwise, you have to control the input amount to the mass spectrometer. Okay, but in a capillary column, there is a very small amount of species, and so you can directly connect this capillary column in gas chromatography to the inlet of a mass spectrometer. But for the liquid chromatography, since this one creates a huge volume of gas when solvent vaporizes at the interface between the column and the mass spectrometer. Now, let me tell you the difference between the gas chromatography and liquid chromatography. Difference is that which one is the carrier? In gas chromatography, carrier is gas. But liquid chromatography, carrier is liquid. Okay, so liquid, once it vaporizes, the volume expands more than 1,000 times. Okay, so for the liquid chromatography and mass spectrometry, you need to do something to inject the sample to the mass spectrometer. Okay, but for the gas chromatography with the capillary column, there is no need for that. For the liquid chromatography and mass spectrometry, you need ionization method. There are different ionization methods: electrospray ionization, atmospheric pressure chemical ionization, and non-volatile mobile phase additives, and such as phosphate buffer, which are common in chromatography, must be avoided for mass spectrometry. Okay, this is important. Non-volatile mobile phase additives, right? Non-volatile mobile phase additives should be avoided, right? For the mass spectrometry. Volatile buffer components and additives for liquid chromatography that are compatible with mass spectrometry include. So non-volatile, this phosphate buffer is one of the most widely used buffers in chemistry, but it is not adequate for mass spectrometry. But other buffer components, like ammonia, and this is what the formic acid and acetic acid, and this one is trichloroacetic acid, and this is amine, and they are all amines. They are quite volatile. Okay, at high temperature. They are okay. They can be introduced to mass spectrometry. Okay, let's first consider the electrospray ionization. It is also called ion spray. Look at this. This part is from liquid chromatography, and this part is mass spectrometer. Okay, and you need interface between liquid chromatography and this mass spectrometer. Okay, let's look at this part. And here, liquid from chromatograph. Now this is a nebulizer. it pass through this nebulizer, and then nebulizer is this part is grounded, and this chamber is negatively that the potential is applied. How negative is usually minus 3500 volts. Okay, and this is called a spray chamber. And with your sample in the nebulizer, the samples are separate samples are sprayed into this chamber, and then along with this one, you use this dry nitrogen gas here, and then with this one, this dry nitrogen gas, and then here your separated your sample is becomes fine aerosol. Okay, and then important is that it is charged, because in this chamber, the chamber itself is negatively charged, negative potential is applied, and this one, this nebulizer is grounded. So under this high potential difference, your samples are charged, okay, and becomes fine aerosol, and then it enters this one, this part. This is gas capillary, very thin capillary, and then most of your samples are drained through this one, this hole, and very small amount of your sample enters this glass capillary, and also this glass capillary is the potential is applied, and then extremely small amount of your sample, already charged samples, now enters this skimmer. This is skimmer cone. A skimmer, it rejects most of samples, and only a very extremely small amount of your sample now enters to pass through this part. This is called electrostatic lenses, focus and collimate ions. Okay, these ions are focused and collimate and enters to this, in this case, quadrupole mesos separator, and is detected. Okay, this is actually quite complicated. So LC-MS, that instrument is very, very, very expensive. Okay, well, liquid from the chromatography column enters the steel nebulizer capillary here. Okay, at the upper left here, along with coaxial flow of nitrogen gas here. It is important to you also you flow this dry nitrogen gas. For positive ion mass spectrometry, the nebulizer is held at 0 volt. The spray chamber is held at minus 3500 volt. Okay, for creating the negative ions, this potential is reversed. Here, this chamber is grounded, and this nebulizer is applied to negative 3500 volt. Okay, and here at this part, collisionally activated dissociation occurs between capillary and the skimmer. Okay, you will see soon. Typically, but not always, ions that vaporize from aerosol droplets or already in solution in the chromatographic column. Okay, here, you see, now your sample already separated by liquid chromatography, and then it enters this nebulizer and sprayed, and then it becomes fine aerosol, but it may be already contains ions. Okay, vaporized aerosol droplets are already in solution, and it has already ions let me see, for example, this one, this ion, yeah? This is a molecule, yeah? And it it has protons, right? So total mass is n plus 1, or sometimes it contains potassium ion, right? So total mass is n plus 39, yeah? Potassium ion mass is usually 39, and or it may contain ammonium ion, or this one, this formate, right? And sodium ion, acetate, right? You see, this sodium, this ammonium ions and potassium ions, these ions are very common, right? Even in air, there are sodium or potassium or ammonium or hydrogen or proton ions, okay? All right, so when you interpret the mass spectrum, you have to consider whether it may contain the proton or ammonium or sodium, something like that. Yeah? So although at first you may be wonder that why the molecular mass is different, yeah? That's because the molecule contains these additional ions. Okay, for protein electrospray, it is common to find multiply charged ions, such as this molecular plus n protons. Okay, so total charge is n plus. Yeah? Okay, yeah, that is usual case, or sometimes maybe sodium ion. Okay, or sometimes n ammonium ions. Okay, but in this technique, this electrospray ionization, usually there is little fragmentation in electrospray. Okay, let's look at this blow up the figure. This is metal capillary. Okay, then in a high voltage is applied. And this is a nebulizer. This is inlet to let me see. I'm sorry. This is not. Let me see. Not nebulizer. This is the metal. This capillary, and here this is the inlet to mass spectrometer, and here the liquid now contains and participant negative ions, and this is a Taylor cone, and this is the shape, between the metal capillary and the inlet to the mass spectrometer. And then now here you apply the very high voltage between these two plates, right? And then eventually these gas phase ions are entering to the mass spectrometer. Okay, adjusting the schema cone voltage controls the degree of fragmentation. A small voltage difference favors molecular ion, whereas a large voltage difference creates fragments that aid in identification of analyte. Okay, here this part is this one, this blow up the part. Okay, well, and now let's consider collisionally activated dissociation. Dissociation occurs in the region between the glass capillary and the schema cone. Background gas is usually nitrogen. Yes, as you also you have to use the dry nitrogen gas. Adjusting the schema cone voltage controls the degree of fragmentation. Okay, a small voltage difference favors molecular ions. Okay, so here schema voltage is this one. Okay, this is schema. Now in this figure, schema voltage minus 20 volt is applied. Okay, but by controlling this schema voltage, you can create fragmentation or not. Okay, and with the small voltage difference, usually molecular ions are formed. whereas a large voltage difference creates fragments that aid in identification of an light. So, fragmentation is not always bad, right? With the fragmentation pattern, we can infer the molecular structure. Yeah, here is an example. This acetoaminophen, yeah, actually the structure itself is not very complex, okay? But here, this one is positively, see, when you apply minus 20 volt to the skimmer, right? And then this one, positive ions are formed, but when you apply positive voltage to the skimmer, and then negative ions are formed, okay? And let me see, this one is fragmented, okay? This one, positively charged acetoaminophen may be fragmented, okay, at higher voltage, okay? This is what? This is molecular ion. Yeah? Actually, it is proton. One proton is added, so mass to charge ratio is 152 for this ion. Okay? But when you increase the voltage to the schema, and then it is fragmented. Yeah? This part is removed, so it becomes this one. What is the ammonium 1, 2, 3, 4 ammonium maybe phenol, right? So at the low voltage, this peak increases, this peak decreases. Yeah, this is mass to charge is smaller because this part is removed. Yeah, but at higher voltage, this one decreases and fragmented. This peak is increases. Okay. But when you apply positive voltage, if you apply the small positive voltage, this one increases and this fragmented this peak it decreases, but at high positive voltage, this one decreases and this peak is increases. Okay, because of fragmentation. Okay. Okay, let's stop here.